All right, welcome to kind of our demonstration and walkthrough video here for some of our Crystal Lab examples. Uh, Kind of our purpose today, since you're not going to be in person for this experiment, there's not really an actual experiment to be done. It's more just kind of looking at crystal structures and kind of trying to identify structure types visually, and then being able to do some calculations that kind of pertain to that or give information pertaining to those crystal structures. And so what I'm going to kind of do here today is I've got kind of our actual, basically our printout for our lab. Like if you go to your questions printout for your lab in D2L, this is kind of what I have up here. And I'm just going to go through and I'm going to kind of fill out some of these pieces for a lot of these examples. And at the very least, I'm going to show you every single crystal structure type. So I'm going to have kind of our actual Gaussian program that we normally use when you're here in person to show you the structure types. We'll talk a little bit about what kind of the structure types are and help you kind of identify what you're looking at, kind of go through what are the different pieces that CSE Pub is going to be then looking for. And really what you're going to see in your actual post-lab assignments is all of these kind of lines here. Those are kind of separate individual questions on CSE Pub. And I'll kind of also show some things as far as where some other pieces of information might come from in terms of being able to do like density and radius calculations. You do need some pieces of information that come from the pre-lab reading, which I also have open that I'll kind of pull up and show where some of the useful tables for some of those calculations are as well. I'm not going to show you absolutely everything for the whole assignment because I do want you guys still to hopefully kind of develop some kind of understanding, kind of working knowledge of what you're doing with these structures on your own. But hopefully I'll give you enough here to kind of get you started and hopefully kind of, like I said, have a feel for what it is you're trying to do from an information standpoint and take away from all of these structures for right now. So that when you go to work on this on your own, you can do most of it, and then hopefully have maybe just a couple specific questions for your individual faculty members when you have your lab meetings this week. With a lot of people doing their virtual meetings. So what are we going to be looking at then? I'm going to start with our first example of polonium, and I'm just going to go through kind of all the pieces. And I think the pre-lab video does a little bit of this already, so I'm not going to go through huge details here on polonium. I'll spend more time probably on some of our other examples. But I'm going to go through kind of just what all the pieces are out of this table. So the first part for polonium, we're identifying the unit cell type. So here is our image. And remember, for unit cell types, we really only have 4 that we ever kind of talk about in this class. And really, we only kind of focus mainly on the 3 cubic ones, even of those 4. But our 4 main options, we can have simple cubic, body-centered cubic, face-centered cubic for unit cells, or we could have hexagonal. This one's pretty clearly cubic. It has a cubic structure to it, just based on kind of how all of the atoms are arranged. And in terms of whether then it's like body-centered or face-centered or just simple cubic, has to do with kind of where things are, right? And so in this case, if we have atoms like on faces, then that obviously then becomes face-centered cubic. If we had one extra atom that's kind of in the dead center of the cube on top of just things in the corners, that would be body-centered. Or we can have this instance, which is going to be kind of our simple cubic example, or you might hear it referred to as primitive cubic sometimes. Simple cubic and primitive cubic are pretty much the same thing. Once upon a time, crystallographers tried to use those simple and primitive to kind of differentiate between packing styles and unit cells, I think. I don't think that's really necessarily the case anymore. I think most people anymore just really refer to everything kind of as simple cubic for both the packing style and the unit cell type because there are some slight differences there. Remember, like for instance, for a face-centered cubic unit cell, it comes from the cubic closest packed packing style. And so that's kind of what I mean in terms of like how those things can be different. But like simple and primitive cubic, like I said, they're pretty interchangeable these days, and most people tend to just talk about simple cubic as kind of the structure type, whether it's unit cell or packing style anymore. And so this is going to be an example of a simple cubic unit cell. And so in terms of this question, like on CSE Pub for your post-lab assignment, you are going to see this as a multiple choice question, and you're just going to look for the one where your answer is going to be simple cubic. And again, if it doesn't have simple cubic, it'll have primitive cubic instead, and you can select primitive. I honestly don't, unfortunately, remember whether it has the simple or primitive option. I think it's simple, but if it does say primitive instead, just be aware, simple cubic, primitive cubic, we use those pretty much interchangeably in terms of kind of how we approach things typically for this class. All right, the other things then this is going to ask for CSE Pub, we have this Z. So what this Z is, remember, is this is going to be the number of atoms inside the unit cell. So if I'm looking at this structure, I want to know how much of all these atoms in the corners are actually inside that individual cube itself. And it's important because we don't, like Z here is not 8, right? All these atoms in the corners are not entirely inside this cube. So it's not going to be 8. We have to figure out like what fraction of each of these is inside the unit cell. And one of the ways that I usually like to think about this is just think about, at that location on the cube that that atom's located, how many total cubes meet at that one little point. And if we're looking at corners, turns out that should be the meeting point of 8 total cubes. If we expanded this out to kind of, in 3 dimensions beyond a single unit cell, we could have 8 total cubes meeting at every corner, which means there's really only 1/8 of each of these atoms in the corners inside the 1 unit cell that we're looking at, which conveniently the math works out nicely. If we have 8 corners and it's 1/8 of an atom each, that means our Z for a simple cubic structure should just be 1. We have a total of 1 full atom inside the unit cell. And if we remember that the corners kind of all add up to 1, that makes finding Z for like our other structure types a lot easier when we see like our body-centered cubic and our face-centered cubic examples that'll be coming up here shortly. All right, coordination number is what this CN stands for. It's kind of the next blank here in this chart. And so coordination number can be a little bit hard to see from these images. And so a lot of times I will often refer back to the packing styles because I think it's easier to see those. And the pre-lab, I think, does a decent job kind of highlighting some of those. But the nice thing is it's also kind of always pattern-based. Like if you know your structure type is simple cubic, Z will always be 1, and your coordination number should always be 6. And there aren't going to be any exceptions to that unless we're looking at ionic compounds, in which case the coordination numbers will work a little bit different, but we'll get to that kind of as we go. Now, if we're looking at the structure and trying to figure out like where in the world does 6 come from for a coordination number, let's say I look at this corner atom right here. This is touching the 3 atoms it's got lines kind of connecting things to, so that's 3. But the other 3, in order to kind of figure out where are the other 3 things that atom is touching, you need to expand your picture out in 3 dimensions. And what I mean by that is you have to consider your other neighboring cubes. So you'd really have one atom also that would be going up, one that would also be going to the left, and one that would be kind of coming out towards us. So it is going to have a coordination number of 6 with kind of almost an octahedral type geometry around that corner atom. And so that's really where that coordination number is coming from. But again, it's hard to just see that when only looking at a single unit cell. So don't feel bad if you're looking at this like I have no idea where it comes from that structure. It's probably easier just to remember for the packing type. Like if you have a simple cubic structure type, then your coordination number is 6, always. And I do know that means that there's kind of a decent bit of memorization to this chapter. In the case of solids, that is kind of the case. It's kind of hard to get around. There's probably more memorization of some of the solid structure types than there is for kind of a lot of other things that we see, especially early on here in 1212. All right, our other pieces. So for packing efficiency and density, these are actually calculations. I'm not going to show these right here right now because really the pre-lab video walks through both of those calculations for you if you've watched the pre-lab video all the way through. And so I'm not going to show the full calculations, but I will kind of describe how to do them. And then I'll show examples of these calculations for one of our later examples, just to make sure everyone kind of knows how those calculations work, just to kind of give some additional kind of, like I said, feedback kind of walkthroughs to kind of help people along with those types of problems. So for things like packing efficiency, how this is going to work, what you're really trying to calculate, packing efficiency is kind of a general reminder. This is the space that's occupied by the atoms themselves inside the cube divided by the total volume of your whole cube itself, like the whole unit cell. And we really only do these calculations for the cubic unit cells. You could say, it's the volume of the atoms divided by the total volume of the unit cell, which is the real definition. But since we're only looking at the cubic cells, that's why I said kind of the volume of the atoms over the volume of the cube, because that's really how we'll be looking at it for our calculations and our examples. Density then is kind of somewhat similar, but instead of looking at the space occupied, we're looking at the mass of the atoms inside the cell. So the fact that we have exactly one atom in the cell, we can take the mass of a single atom of polonium, which will be really, really tiny if our units are going to be in grams for the mass, and divide that by then the volume that's going to be in cubic centimeters, which is also going to be really tiny. And probably with this calculation, this is the one where it's easiest to make a mistake, but it's also easiest to recognize when you've probably made one with the units, because you're going to get an answer that doesn't make a lot of sense. Most densities are probably going to be somewhere between, maybe on the low end, like around like 0.2 or 0.3 for any examples of things that we would see, up to on the high end, maybe like 20 to 25. You're not going to see things that are like 10 million or, like something times 10 to the minus fourth. Like you're not going to see that for any densities for any of the things that we look at in this class. So if you're getting densities that are really big or really small, pretty much can guarantee it's a unit mismatch issue where you haven't converted your units properly. And so that's something good to pay attention to. If you get something that's just like astronomically big or small, like to like, the -48th or something like that, probably you have a power of 10 issue in how you put things in your calculator. So just be very, very careful about parentheses and things like that. And I'll kind of re-emphasize this and show where some common mistakes can happen when I do a full walkthrough example kind of these two calculations for sodium that we'll look at next. And then the last calculation here, the radius of the atom, I will show this quickly here as well. This one's actually fairly fast. For any structure type, so in the case of simple cubic is going to have an equation, and all of our different structure types have equations that relate the edge length to the radius. So in the case of simple cubic, the edge length of the cube itself is going to be 2 times the radius of the atom. Because if these atoms were drawn to their full actual size, like this atom is really going to be touching this one. So this whole length of the edge of the cube is 2 times the radius of the atom, because we basically have one radius that then touches the other for the length of that edge. And so I can use this equation to find the radius, because in our reading, the A value is given for every one of our structures that we're going to look at. So I will show that real quick here. I'm going to pull up, this is the pre-lab reading. So if you go to your pre-lab assignment folder for the Crystal Lab on D2L, open that, and then there's one that's like the pre-lab reading. That's what this document is that I'm kind of scrolling through. And it is a ways down that you're going to find these tables, but you're going to find 2 pretty important tables. Here is one. This has all of the unit cell edge lengths. That's what these are, is the edge lengths over here for all of the different structures we're going to look at today. And then if you actually go down a little bit further, there's another table that has ion radii, which is something we'll use when we get to the ionic examples. And so those tables with those values are in your pre-lab reading if you're looking for them as you go to do calculations. But here in the case of sodium, we have an edge length that's 0.424 nanometers. And so what I can do is, here if I'm looking at A, I know that A is 0.424 nanometers. Now I can just rearrange and solve that equation for R to get the radius of my atom. Right? So that's all I would have to do in that case. And for our other different structure types, this equation is going to be different. And that's the important part to kind of realize, is that these edge length equations in terms of how they relate to radii of atoms, it does change depending on the structure type that we look at. So what I'm going to do is let's move on to looking at sodium. We'll take a look at its image here for its structure in just a second, and I'll go through all of the pieces for sodium so that we can actually see some examples of that, the packing efficiency and the density calculations as well. All right, so that's our polonium structure. So let me go ahead and actually open our structure for sodium. So just sodium, here we go. So sodium looks like this, and I can zoom in maybe just a little here. And if I'm trying to describe the structure, it looks like we again have atoms on all of the corners of a cube type shape, plus we have one that's kind of sitting in the dead center. So if I'm trying to describe what the shape or what the unit cell type is for sodium, my description of the sodium structure unit cell type should be body-centered cubic. Right? Because I have the one atom that's sitting in the dead center of my cubic unit cell. And now to go through my other pieces for the Z, well, if the simple cubic had 1 for all the atoms in the corners, that's still the case here, right? All the atoms in the corners all added together should be 1. And then I have the one that's in the dead center that's fully inside my unit cell also, which is going to make my Z be 2 for all of my body-centered cubic cells. So anytime you have a body-centered cubic unit cell, Z is always going to be 2. And then in terms of my coordination number, this is actually a little bit easier to see in the unit cell, because in terms of what things are actually touching, all of your atoms that are on the corners are touching this one that's right here in the dead center. So this one is actually touching all 8 of the atoms that are on the corners. And so the coordination number is actually 8. And that's true for all of the atoms in the structure. It's just for the ones in the corners, you can't really see that unless you look at the neighboring cubes. And I guess just to point it out kind of quickly, remember we said the corners of the cubes are the meeting spot of 8 cubes? Well, atoms in the corners are kind of like the dead center position, where basically the center atom of those 8 cubes that are meeting at this corner or would be at the corners of a different cube, and this would be touching all 8 of them. And so it still has a coordination number of 8 as well. You can just kind of do almost a perspective shift to see that. We can't really do that here with only the one unit cell shown, which is fine. But all of these atoms in this structure are going to have that same coordination number of 8. Now, I said I did want to do the calculations for packing efficiency and the density and the radius. So for packing efficiency, in terms of kind of showing how this is going to work, I'm going to try and zoom in and hopefully not take up too much space as I go through this. Packing efficiency, how we calculate this. Remember, this is going to be calculated by taking the space of your atoms divided by the total volume of your entire cube. So how do we find those things? In terms of our atoms, right, the volume, so I'll write this volume of atoms over the volume of the cell, or in this case, our cube. Well, if we think about our atoms, what kind of shape do they all have? It's kind of a spherical shape, right? So what we can do for all of our atoms is we can basically say that our volume of our atoms is going to be the number of atoms, which in this case is 2, times then the equation we can use to find the volume of a single atom. We're just going to use the volume of a sphere equation, which is 4/3 pi r cubed, right? Would be the normal equation we can use for the volume of a sphere, except I can go ahead and actually write in my volume here that my R for my packing efficiency for sodium is I'll actually show where I'm going to get that value from in just a second. But basically, I'm going to take that value, I'm going to cube it. And then I'm going to divide all of that by my volume of my unit cell, which is going to be my edge length cubed. And so I'm going to show you where I'm going to get these two values, right? Because before we said that for all of our different packing styles or different unit cell types, there's the different edge length equations for A. Well, A itself is the value we can get from our pre-lab reading. So I can look up A in here for sodium. A is the 0.42. Actually, I think I showed this number above for polonium, so I will go back and fix that quickly here in just a second. 0.424 for sodium. That's my edge length for sodium. So let me come here. I'm going to say A is 0.424. Let me scroll back up. That polonium example, let me fix that. This was, I believe, 0.336. So sorry about that. So that's the number you'll use here as A to then find the R for polonium. I apologize for kind of mixing those two numbers together. All right, so coming back here then for sodium, if this is my A value, the thing I want to keep in mind is that for a body-centered cubic unit cell, A is not 2R, but A is actually going to be 4 times R over the square root of 3. And so now if I solve this equation for R is going to be 0.424 times the square root of 3, all divided by 4. And now I can find what that R value should be. And so I'm just going to take a second and actually calculate that. And I get about 0.184 nanometers, since that was my starting unit here for the edge length itself was in nanometers. And so I can come up here and say 0.184 nanometers is going to be cubed. And I can leave this in nanometers as long as then oops, actually I'm kind of getting ahead of myself here. Make sure I'm going to put the right value in the right spot. 0.184 is my radius, right? So this is R. So R is the 0.184. That's going to go in the top of my equation up here. This is in units of nanometers. And on the bottom is going to be that full edge length, 0.424. Right, so in this equation for my packing efficiency, the volume of the atoms uses the radius that we're finding, because that's what we use for this 4/3 pi r cubed equation to find the volume of a sphere, which is our atoms. We treat them as spheres. And then I use the 0.424, which is the edge length of my overall unit cell. I'm just going to cube that because that's going to give me then the volume of the whole cube. Right, a cube's volume is just the edge length cubed. All right, and now I have everything I need to go ahead and plug in here, and I can find what my packing efficiency is. And if I've done everything correctly, my packing efficiency should always be less than 1. And in fact, I actually already know for body-centered cubic, I believe it's somewhere around 0.68, so hopefully I'm going to come out something very close to that. And if I don't, then I've messed something up here and it's kind of going through this. And that's what I get, is I get about 0.685 and with the numbers that I'm using. Now, I will say this lab has in the past had some issues in terms of not being very forgiving for any rounding that happens. So if you do run into any issues in terms of like rounding, please feel free to reach out to your instructors or myself, Dr. Meyer, and I can kind of help out and look and make sure that it's an issue, like whether it's on CSC PubZin or whether you actually did something different with the calculation itself. There have been some times where like if you're off by, maybe like the just a little bit in like the last decimal place. Sometimes it's really picky. So do try to use the exact numbers that are given like in the tables in the reading, because that's where all the CSE pub calculations come from. And if you round those a little bit too much, then sometimes you can run into issues. But if you do get things that are really, really close and just off by a tiny, tiny bit, feel free to reach out to us and we can take a look. And in a lot of cases, we might end up giving points back if it's just kind of some quirky things on CSE pubs. And that has happened with this lab in the past. I think it's a little bit better in a lot of our future labs, hopefully now. But I'm not sure if all of the kinks have quite been worked out with this particular one. All right, so that gets us through all of our packing efficiency calculation here. And one of the nice things about packing efficiency, in terms of kind of like lecture applications as well, is that packing efficiency actually doesn't depend on the element involved. And what I mean by that is if you have a body-centered cubic unit cell, your packing efficiency is always going to be this same value, about 68% or 0.685 in that range. It's never going to be really anything much different than that. And the reason for that is because if we think about it, this edge length that's getting cubed down here has basically R in it. It's in that equation, right? That 4R over the square root of 3 equation for the edge length. Here we have R being cubed. If you kind of rewrite A that's being cubed down here as that 4R over the square root of 3, the R's can all just cancel out entirely. And you're basically like the actual size of your atom doesn't matter. Because you know the structure type, your packing efficiency will always be the same. And that'll be the case for all of the structure types, as long as it's a pure metal. Ionic ones get a little bit different, but we tend not to do much with packing efficiency on the ionic examples, because there's a lot of other factors, a couple of which I'll mention when we get to them, that make that a little bit more complicated to actually try and be able to do. All right, now, in terms of our density calculation here, which is the other calculation portion. So density is going to be our mass over our volume. And so in terms of how do we go about finding that? For our mass, your mass calculation step is always going to be the number of atoms that you have. So your Z, which if I zoom out for a second, our Z was 2. Right? So if I go back in here, zoom back in as I kind of write all this, I have 2 atoms times then the molar mass of the element involved, which in this case is sodium. And I believe the molar mass of sodium is about just under 23. 22.99, so 2 atoms times 22.99 grams per mole. And let me rewrite that maybe just a little bit clearer, so it shows up a little bit neater here. So 22.99 grams per mole. Then times one other thing, because if I'm looking at my units, I have 2 atoms times something that has units of grams over moles. My units are all over the place here, right? I really only want grams, so I need to cancel moles and atoms out of this somehow. So I need a ratio that's going to have atoms on bottom and moles on top. And what relates those? Well, the only thing that relates moles and atoms is Avogadro's number, where 1 mole is that 6.022 times 10 to the 23rd, right? That's Avogadro's number, atoms. And so that's where all of this now together is going to give me, if I'm looking at my units, the moles will cancel, the atoms will cancel, I will just get grams. And it is going to be a really, really tiny number. Do expect a very, very, very small number out of that. Now, for the volume side of things, this is actually easier. It's going to look exactly like it did in the previous one for the packing efficiency. It's just the edge length cubed. I already had that, but I have one thing I have to be careful of. Remember, for density in the units that were asked for, the units that it asked for over here, if I scroll over enough for us to see it, are grams per cubic centimeter. So for me to get those for my units, I need my volume in centimeters, basically, before I cube it instead of nanometers. And so I can rewrite that, and hopefully people are a little more comfortable doing those conversions these days. But I'm just going to do this. I know that nano is 10 to the minus 9, centa is 10 to the minus 2. So it's like a 10 to the minus 7 difference kind of going in that direction. And so really, I'm just going to write this as 0.424 times 10 to the minus 7 centimeters that I'm then going to be cubing. And if you need more help with this, feel free to reach out to your instructors or myself, like as you're going through kind of this lab for unit conversion kind of refreshers. That is something from 1211 that probably still expected to be able to do for 1212 as well. And you can kind of, I always set it up with just like dimensional analysis, right? So I'll show it kind of just very, very briefly up here in the upper corner. But like if you're in units of nanometers, you can always remember kind of do a two-step process where if you know the relationship between meters and nanometers, then you can use the relationship between centimeters and meters. And now you just have to put in, what are the ratios of these units for our dimensional analysis. In the case of meters, there's 10 to the minus 9 meters in 1 nanometer. For centimeters, 1 centimeter is 10 to the minus 2 meters. And so we end up with, this is going to be like 10 to the minus 7 in terms of our units for the centimeters kind of at the end. So whatever we had in nanometers, we're multiplying it by 10 to the minus 7th to get it to centimeters. And that's kind of what I showed here. Now, the numbers we do get out for this, just to kind of give you some perspective, I do want to show these numbers. So for density, the actual mass, if I calculate just the mass part of this, so we can get kind of a rough estimate for what size numbers we actually expect. I get a mass that's about 7.63, let's call it 7.635 times 10 to the minus 23. That's in grams. I'm going to divide that by a volume that's 0.424 to the minus 7. Going to be cubed then. And I get about 7.622, looks like 23 maybe, times 10 to the minus 23 cubic centimeters. Right? Those are really, really tiny numbers. And if I actually then combine those to find a density, I know I'm kind of scrunched in here a little bit. Let me zoom in so I can maybe write this number a little bit better. But then the actual density, if I take my mass divided by my volume, it's going to be really, really close to 1. Really looks like it's about maybe 1.0, almost 1.001 actually grams per cubic centimeter, or almost 1.00, depending on how many sig figs it's really asking for. Probably only really wants 3, so maybe 1.00. If you put in 1.00 grams per cubic centimeter and CSC Pub tells you it's wrong, do reach out to us and let us know. It's really easy for these to maybe off by a decimal, and sometimes CSC Pub, like I said, for this lab in particular, I do know it's had issues in the past with being picky about some of those sig figs. All right, but that is how we get to our density. Like I said, the radius we actually already found. We showed that for the packing efficiency part to be able to have our R value, and that's kind of what our calculations are going to look like. So for platinum, I'm not going to show the full calculations kind of going through them, but I will talk about the structure type itself and kind of help out with like the Z and the coordination number a little bit and refresh people of the radius of the atom equation, hopefully, that you should be using. And then I'll talk about some of the ionic compounds and kind of what's different, because I think it's important to recognize the base structure types of pure metals before looking at ionic examples, because ionic examples kind of start with our base structure types, but then add more to it. So like I said, I want to hopefully make sure everyone kind of knows what our pieces are for each of these different things we're looking at. So in the case of platinum, let me go back and pull up our structure for platinum. So for platinum, what we're going to end up doing here, let me open up its structure. Platinum. So here we have one that looks a little bit different. Again, I'm going to kind of zoom in a little bit and kind of center it some more. So if I'm looking at the structure and trying to describe what exactly it is that I see, I do see a cube, and I actually have lines kind of connecting things to help me see it a little bit. I have my cube with all my atoms at the corners. Then I want to figure out, well, where are all these other atoms? And it looks like if I pay close attention, all these other atoms are on the faces, right? So these other 6 that I clicked on here at various points, those are all the faces of the cube, which means in terms of my structure type for my unit cell, now we're looking at face-centered cubic. All right, so for Z, for face-centered cubic, one of the things to think about is how much of the atoms that are on the faces are actually inside the unit cell. Well, each face is the meeting point of 2 cubes, which means you'll have half of that atom on a face in one cell and half in the other. So if each of the faces adds half of an atom, and we have 6 total faces, that's 3 additional atoms, plus the one that comes from all of the corners, which is why for face-centered cubic, Z is always 4. Now, the next part of this is much, much harder to see from just the actual unit cell, and that's the coordination number. So for face-centered cubic, it turns out the coordination number is actually always 12. But again, looking at just the unit cell, it's almost impossible to actually see where that comes from. And so probably what's more useful in this case is, and I think I talked about this a little bit in some of our pre-lab video, if you understand the packing styles themselves, so in the case of something that's face-centered cubic, its packing arrangement or packing style is cubic closest packed. So if this is, say, a first layer of atoms in a cubic closest packed packing style, I'm going to switch my colors here so we can see a second layer. This would be then where my second layer of atoms ends up going. So it's kind of staggered a little bit in some of the crevices of that first layer. And if it's cubic closest packed, which is where face-centered cubic comes from, there's then a third layer. Oops, I'm clicking the wrong spot to change my color. That's actually going to go in the other cracks. And that's maybe not the best spaced example here, but it's hopefully close for people to see where it's organized. And if you're trying to picture how we get coordination number, if you imagine that the blue spheres are actually underneath that first black layer I drew, and that the red spheres are kind of on top, that would be one way to consider what this would actually look like, or vice versa. If the red are on bottom and the blue are on top, it doesn't really make much of a difference. And if we look at that very center black sphere here, it's going to be touching all 6 of the black spheres in its original layer that I drew, but then it'll also touch, like, say, the 3 blue ones that would be below and the 3 red ones that would be above, for a total of 12. And that's where this coordination number is actually coming from. And so when you have good images, which I wouldn't exactly call this necessarily a good image, my artistic skills are definitely limited here, unfortunately, then you can kind of see where the coordination number comes from the packing styles, if you think of kind of that layer by layer building approach to the structure. The unit cell itself, when we're looking at this, it's much, much harder to see. And in fact, this unit cell is actually, like, the unit cell itself is actually at kind of like a weird angle. Like this, is probably something in here like at an angle like this almost, in terms of how these different layers are actually affected. And so it's cut at a kind of a very awkward angle for where this face-centered cubic structure comes from. It's not as obvious and easy to pick out as like simple cubic or body-centered usually are. All right, now before I go on to other examples, I think the packing efficiency, the density, again, I'll let you guys kind of work on that one specifically for platinum on your own. The radius of the atom still works the same way. Just remember that for face-centered cubic, our edge length equation is again different. And now we have, you might see this written 2 different ways. You might see it written like this. That's also the same thing as this. So you might see it either way, depending on kind of what reference you actually look at, whether it's pre-lab meeting, or it's pre-lab video material, or the pre-lab reading material, or if it's like, notes from your actual lecture when you get there. These 2 equations are exactly the same. They're just different ways of writing them. So that's you might see either one. I've seen them both, depending on, like I said, kind of the reference. But that's the equation you can use to find the radius from the edge length, if you look up the edge length for platinum from kind of those tables in the pre-lab reading. Now, the other thing I did want to mention, there's space in all of these things that for the 3-dimensional unit cell drawings. When you get to the end of basically the whole lab, it is going to ask you for 3-dimensional drawings of each of these structures. So do these as kind of as best you can, but don't lose too much sleep over like how perfectly drawn they are. Like, do your best to try and draw something that resembles a face-centered cubic cell. Like in the case of platinum, as far as when you're labeling it, like our previous examples, like sodium, do your best to try and draw what a body-centered cubic cell looks like. They don't have to be perfect. My artistic skills are extremely limited, so I don't have high expectations here. Most of us that teach chemistry, artistic skills are usually probably not the greatest, because we tend to be more science-based and maybe not always the best at art. I won't speak for everyone, because I know there are some people in our department who do have very nice artistic abilities in terms of being able to draw very nice pictures for unit cells, orbitals, things like that. I am definitely not among them, so I do not have high expectations for the students to replicate a perfect drawing by hand. But what it's going to do on CSE Pub, it's going to ask you to upload one basically image that has all of your 3-dimensional drawings. So when I'm showing all of these structures, you can kind of go back to the different parts of the video if you need to. Try to make the sketches of what each one looks like, but try to do all of the sketches of the structures on one single page, and then upload that to CSE Pub when it asks for them. CSE Pub will also ask for your work on your packing efficiency and density calculations. So when you're showing the calculations for these 2, I would probably do all of those calculations kind of similarly on a single page, so that you can kind of take a picture of one page of work and just upload that one image into CSE Pub. If you do have any issues with that, feel free to reach out to myself, to your instructor, or you can always just email it to us and we can grade it that way if we have to as well. We have different things that we can do, but ideally I think the thing that makes it easiest is just do all of your 3-dimensional unit cell drawings on a single page, all of your calculations for packing efficiency and density on a single page, and that'll make it easy to kind of upload that work to CSE Pub when it asks for it, kind of towards the end of the post-lab assignment. All right, I think we have one more pure metal example to look at, and this is going to be kind of the weird one of the bunch, and that's going to be zinc. And so I'm going to pull up the structure of zinc, and you'll see why there's fewer boxes there over there on the side for us to actually look at. And so let me open up zinc here. And let me adjust this thing's view a little bit so it doesn't look quite so crazy and spiky. Get rid of that. All right, so here's our image for the structure of zinc. I'm not going to call it a unit cell because the reality is it's actually not a single unit cell. It's actually multiple kind of put together here. And so this is basically our structure for zinc. I'm going to spin this to an angle that might hopefully give us some perspective of what we're looking at a little bit better. There we go. I'm trying to orient things for myself. All right, so in terms of best trying to describe this packing style, notice if I'm looking here in the middle, it kind of looks like what I had drawn up above on my work before. Like when I was drawing this image, how I had like a layer of 6, like one layer that had 6 things around a central atom, like 3 above, 3 below. This looks similar to that, right? I have a central atom, 6 around it in one layer, 3 above, 3 below, except my above and below parts are exactly aligned with each other. So this structure I drew before we said was cubic closest packed, which gave us the face-centered cubic unit cell. When the above and below layers kind of to your original one are basically like eclipsed, like right on top of each other and not staggered and offset like the previous example, then this structure here is actually hexagonal closest packed, which means my unit cell type is actually going to be hexagonal when I go to write this in. Now, this is the structure type we talk the least about in lecture and probably just in general in this class because calculations become much more complicated because our unit cell isn't a cube. And so calculating things like volume and looking at how many atoms are in the cell becomes much more difficult. And these are things that I usually just end up kind of telling our lecture sections is that Z is always 2 for a hexagonal unit cell. And you might be looking at this and it's like, well, how in the world does that work? This is not a single unit cell. This is actually multiple unit cells, like 6 or 7 unit cells, kind of all combined together, just to give kind of a bigger cohesive image to better hopefully see kind of this hexagonal packing style. Now, things you can pick out. Coordination number, with the way I have it set up, might be a little bit easier, right? If this is my central atom right here, I have the 6 around it in the same layer. I have 3 in a bottom layer below, 3 in a top layer above, all that are going to be touching this one atom, which means this coordination number is 12, just like we saw for face-centered cubic. And then the last part, the radius of the atom, it turns out that for zinc anyway, A, which is not just it's a little more complicated being hexagonal, but the general equation we often talk about for hexagonal is that A, your kind of standard edge length, not the one that's kind of the different length for the hexagonal unit cell. A is equal to 2R. And so the edge length that you're actually given in the pre-lab reading, like if you look it up, there is an edge length that's given here. This is what you can use along with this equation for hexagonal to find the radius of your atom. And so you can find it using this. But again, I think this is the unit cell type we do the least with. You notice there's no packing efficiency or density calculation. There wasn't even an image of the individual single unit cell anywhere kind of in here for it because the unit cell for hexagonal does look kind of wonky. It's not a cube. You have kind of one edge that's elongated from the others, and you have angles that are not all 90 degrees. And so it is kind of it's a quadrilateral in terms of like the fact that it has like, 6 faces, kind of 4 by 4 or 4 edges to all of its different faces. But since it doesn't have 90-degree angles, it's definitely not a cube. It's a little more complicated to do a lot of those calculations, which is why we're not going to make you do more than kind of just the bits that it's asking for right here. And in terms of the 3-dimensional unit cell drawing, I think the version that I had here, hopefully it's probably the easiest one to draw. Kind of like I said, you have like a single layer with six atoms making kind of a honeycomb arrangement around a central one, like 3 above and 3 below that are basically on top of each other in terms of their arrangements. All right, that gets us through all of our pure metal examples. I also want to take a look at some ionic examples and kind of what those are going to look like as well. So to take a look at some of those ionic examples, let's first start with cesium chloride. And we're going to notice some of the things that CSE Pub is going to ask for are a little bit different. And so I want to make sure that everyone is comfortable and aware of what those pieces are. And then I'll go through some sample calculations for this as well. And I will go through the calculations here for cesium chloride specifically. Oops, there we go. Because I believe the pre-lab looks at doing the calculations for sodium chloride. And that way you can just see some, again, different examples of how things are working. And hopefully give you guys a better understanding of a lot of this, because we're well aware that your lectures are probably not going to get to this solid material stuff next week when you're going to be doing some of this stuff for the lab still. And so we're trying to kind of cover that as much as we can here in the lab, kind of with some of these videos, because we are aware of that fact. Scheduling this semester is just a little bit awkward in terms of kind of the timing, because we've lost a week total from our normal semesters. And so things are a little unfortunately kind of offset here at the start of the semester, and we should hopefully get back to a better pacing of things in terms of the lab and lecture kind of syncing up topic-wise as we go further along. All right, so looking at our structure that we do have here, this is the structure of cesium chloride. Now, ionic compounds are different in the way that we talk about their actual structure types, because notice when you're asked here about the crystal structure for cesium chloride, it asks for a structure type of your cesium ions and a structure type of your chloride ions. And so they each have kind of different arrangements or ways that we talk about them. For your anions are almost always going to have a structure type that is one of those four we already saw for our pure metals. So the anions will usually have a structure type that either looks simple cubic or body-centered cubic or face-centered cubic for just the anion by itself. And so in this picture, the green little spheres here are actually all of our chlorides, and the purple one in the middle is going to be our cesium. And these images are not always drawn to scale. Cesium is also kind of an unusually big cation, but in general, we talk about a structure type of the anion because the anions are normally bigger. Cesium chloride being kind of maybe the one example where they're actually pretty close, and we'll talk about what that can do to things in just a second. But if I look at only my green spheres in this structure, I want to describe for my structure type of chloride ions, what are the structure to just the chlorides by themselves make? Well, the chlorides are only on the corners and nowhere else. So my structure description for those chloride ions should just be simple cubic. Oops. And then for my cesium ions, your cations have one of three possibilities. There's a whole type that we often talk about our cations going into. So when we have these structures like simple cubic and body-centered cubic and face-centered cubic, we saw that their packing efficiencies weren't 1, right? They weren't 100% filled. There was empty space. So what happens for ionic compounds, since the cations are generally smaller, they usually just fit into the holes or the empty space that normally exists in the lattice structure made by the anions. When this happens, your structure ends up a little bit warped in terms of its dimensions, which is why we don't do the packing efficiency calculations as much, and why the density calculations for the ionic examples, you already just have the edge length, so you don't have to find any kind of radii stuff. You just use the edge length to find the density for those examples. But to identify what type of hole a cation is in, it's all about its coordination number. So we basically want to figure out for this central atom, how many things around it is it touching? Or the other way to think about that, how many things around it for the ones that are around it, which ones are closest, and how many look like they're all about that same distance? Well, in this example, all of the corners are the same distance from this one cation in the middle, which means that this cation in the middle should be touching all 8 of the other chlorines that are there, which means the coordination number of this cation should be 8. And when you look at your table over here, there's a Cn+. Cn+ is the coordination number of your cation, which is, we're saying 8. And the pattern you're going to see is whatever your coordination number of your cation is, that's going to tell you the whole type description of what the structure for your cation is. So how that correlation is going to work, if the coordination number of your cation is 8, that's what we call a cubic hole for a structure type. If the coordination number of your cation is 6, that's going to be an octahedral hole. And if your coordination number of your cation is 4, that's then going to be a tetrahedral hole. And while there are other hole types that exist, for our cubic unit cells, these are the only 3 that we really see. And so we're not going to kind of discuss any other options for general chemistry If this structure stuff is something you really like and want to know more about, there's higher level classes that can dive into some of those things. And like I said, for us, these are kind of the three main hole types we're going to explore. And the other correlation you're going to see between these is the bigger your coordination number of the cation, the coordination number is bigger because the cation itself is bigger. So this is the biggest hole type is going to be our cubic hole. And our smallest hole is going to be the tetrahedral hole because it has the smallest coordination number. Basically, the bigger your cation is, the more negative charges you can pack around it without the negative charges getting so close that they repel each other. Because if your cation here is really, really tiny, you can't pack a whole bunch of negative charges around it because the negative charges get too close to each other and it won't be very stable. So the smaller your cation, the smaller its coordination number, and then the smaller the hole type, so it'll be more like a tetrahedral hole for the smaller cations. The bigger our cations are, then we're more likely to have, say, maybe a cubic hole, with octahedral hole kind of being in the middle somewhere. So in this example, if we said our Cn plus was 8, if our coordination number for the metal, for the cation is 8, then we're going to have a cubic hole as our description for that cesium ion. All right, and then for our other pieces that were asked here, we have R plus over R minus. This is something called a radius ratio. This is also another predictive factor to help you figure out the hole type. But where this number is coming from, it's actually just a number we calculate. Again, if you go back to your pre-lab reading, there's the table that has all the edge lengths. And then a little bit further down, remember I said there's another table that has all the ion radii. Basically, that R plus over R minus is just that. You're going to take the radius of your cation, which our example we're looking at is cesium and chloride. So the cesium, the cation is 0.167. The anion for the chloride is 0.181. So our R plus over R minus is going to be just that 0.167 over 0.181, which is equal to, if I calculate that out, 0.923. Right? And it's just a ratio, so it doesn't actually have any units to it. And that would be my radius ratio. The bigger your radius ratio is, usually if it's over about like 0.7 something, it's almost always a cubic hole. If it's kind of between about 0.4 and 0.7, it's usually an octahedral hole. Below 0.4 roughly, it's often a tetrahedral hole. But that's not like 100% accurate. There are some variations sometimes. But that gives you kind of some perspective of, why do we care about this ratio? Well, the closer this ratio is to 1, basically the bigger our cation is, that means we're more likely to have a cubic hole. The smaller this ratio is, the more likely we are to have a tetrahedral hole instead. And so that's kind of why they have you calculate this ratio. All right, last other pieces here from a calculation sense. Z plus and Z minus, we don't actually have to really calculate too much for, but we do still have to look at our structure. So for Z, and really when I'm looking at these, I think Z minus is always the easy one to find because you've already given a structure type for the anion. And whatever your structure type for your anion is, kind of like your metal examples before, if it's simple cubic, the simple cubic metal example, Z was 1. So the Z minus, in this case, the number of anions that's in our structure, that's what the Z minus is going to be just for whatever our simple cubic structure is, which means there's 1 total chloride in my overall unit cell. So Z minus would be 1. And then Z plus, sometimes it'll be easy to identify, like this example. Other times it might not be very obvious. So what I like to do is just look at, all right, if I have CS plus and Cl minus, this is a 1-to-1 ratio, right? Your unit cell has to basically be neutral at all times for it to be your repetitive building block for an ionic compound. So if I have 1 total chloride that I already know based on my simple cubic structure, that means I have 1 -1 charge. That means I should only have 1 cesium plus to balance all of my charge, right? Because like I said, it's a +1 and a -1 charge. So if I have 1 anion, I can only have 1 cation to have my charge be balanced. And that's kind of, easy to see in this because we have the cesium in the dead center. But in the next example, like for sodium chloride, that does get a little bit trickier in terms of how we describe it. All right, now I do want to show the density calculation here, but I want to make sure I have kind of space to hopefully, I think I have enough space here to actually do that. So the density calculation, how are we going to calculate the density for an ionic compound? Well, it's still going to be set up in a similar manner, right? Density is still, in general, mass over volume. The thing we have to keep in track now for our mass is that we have to account for both the cation and the anion that are present, right? So as I set this up, if I'm going to write out for my mass, I want to basically add up the mass of all of my cations and anions that are present. So that means my mass is really going to be like, I have one chlorine atom times chlorine's molar mass, 35.45 grams per mole, plus then the same for my cation. So this is my anion, so I can do the same for my cation. I have one cesium atom times the fact that I have its molar mass, which for cesium, I don't know off the top of my head, is about 132.9. So I can add this together, and then I still, like I did up above, I still have to multiply by that ratio of moles over atoms, which is effectively dividing by Avogadro's number. So I apologize, this is going to be a pretty big space here. So I'm dividing by Avogadro's number, 6.002 times 10 to the minus 23rd. Right on the bottom, this I can think of this as atoms over moles as units. All of this piece that I've just drawn here is just the mass component. Right? Here's the mass of, it's the mass of the chlorine plus the mass of the cesium, dividing by Avogadro's number so that my units are only grams at this point. And I'm going to take all of that divided by my volume, and that's actually still pretty easy because, again, in our pre-lab reading, we do still have the table that even for our ionic compounds just gives us the actual edge length. So for cesium chloride, the edge length is 0.4110 nanometers. So I can come over here and I can just say, 0.4110. Oops, if I can write maybe 110. But I do want it in centimeters, right? We said earlier that if I just multiply by 10 to the minus 7, that's the conversion basically from nanometers to centimeters that I had shown before. So this is now in centimeters, and I'll have to cube that to get my volume. So I'm still going to get some really tiny numbers for my mass and my volume. I will go ahead and calculate those so you can kind of see the steps involved here. So 35.45 times 1 plus 132.9 times 1 divided by Avogadro's number. I get a mass that's about 80 times 10 to the minus 22 grams, all divided by a volume of about 6.94 times 10 to the minus 23 cubic centimeters, which now when I take mass divided by my volume in this case, I get about 4.03 grams per cubic centimeter for a final density. And again, this is a number that hopefully makes sense, right? Our densities, we expect things like, from a little bit less than 1 maybe up to like 20, 25 in the big end. So this is in that range. Again, if you get something that's like 4 million, probably have some unit conversion issues. Most of the time, it's the nanometer and centimeter conversion people aren't careful with, just out of kind of past history of what I've seen. So do kind of be careful with that, and be really careful about parentheses and your powers of 10. Like if you took all of this stuff and found the mass and had this value correct, but then divided by this bottom, and you didn't put, say, all this bottom in parentheses correctly or group all this stuff in the bottom correctly, you might get an answer that's something like, instead of 4.03, your answer might be like 4.03 times, 10 to the, minus like 45 or something crazy, or 46. And so if you're off by just a crazy number of powers of 10, sometimes it's because you weren't careful with your calculator and keeping everything grouped for your powers of 10. Because if you just type in your calculator 2.80 times 10 to the minus 22, and then hit divided by 6.94 times 10 to the minus 23, and don't put all this bottom in parentheses, then it's going to take that 10 to the minus 23 and multiply it on top instead of having it kind of on the bottom of your fraction there. And that's what's going to cause you to be off by 46 powers of 10, which is pretty significant in terms of the size of your answer. So kind of keep those things in mind and just be careful with them as you're doing them. Those are kind of probably the most common mistakes I see on these calculations, are just not being careful with the powers of 10 and the unit conversions, and not being careful with the powers of 10 as you put things in a calculator. Like that's where 90% of the mistakes I usually see on these problems kind of come from. If you are still running into issues with that, not sure where you're kind of going wrong and things, again, feel free to reach out to us. That's really what our virtual meetings this week are going to be for the lab. Is for you to kind of reach out and talk to us and kind of see where maybe you're messing any of those things up, so we can kind of help you get a feel for, like I said, kind of what you're doing with some of these structures. All right, So let's take a look at our last couple structures. I'm going to again walk through kind of how we get the structure type for sodium chloride, but probably not do the actual density portion of it. And then I'll take a look also, I will show the last structure, but the very last structure I would like you guys to identify hopefully on your own, having seen kind of all the things we've seen now for the lab. So I'll pull up the structure here for sodium chloride. Open that quick, NaCl. Probably have to get rid of bonds so that it doesn't look all crazy. All right, so here's what our structure for sodium chloride looks like. And this is one your textbook usually shows as well with some different images. This is actually just a single unit cell. So in terms of getting our description here, the biggest things to kind of pay attention to are really just, all right, let's look at only one color of spheres. And if you click at them, like here I clicked on this one, down in kind of my bottom right, it says like Cl25, so Cl, this is a chlorine, is the green spheres. So the green spheres are chlorines, the purple ones are sodium ions. So looking at just the green spheres, I want to try to figure out what structure do the green spheres make. And it's like, all right, I have spheres here, 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 here. Kind of looks like I do have the corners of all the cube. So I have a cubic structure. And I also have green spheres that, if I'm looking at it, look like they're on all 6 faces of this cube. And so my description for the chloride ions would be then from that face-centered cubic. So I have a face-centered cubic structure for my chloride ions. Now, that also then helps me for my Z minus down below. If I have a face-centered cubic structure for chloride ions, that means for my Z minus, remember before we said if it's a face-centered cubic structure, there should be 6 of that thing inside the unit cell. I'm sorry, not 6, 4. So I should have 4 chloride ions inside my unit cell. That means my Z plus, I should be able to get before I even look at the structure type, right? Because if it's sodium is +1, chloride's -1, it should be a 1-to-1 ratio. So if I have 4 chlorides, that means I also have 4 sodium ions. That's, I think, the easiest way to get the Z plus and Z minus. Because, and if you go to calculate it, we can show that. We basically have sodiums on all of these edges, right? So I have 4 sodiums on edges here. I have 4 more sodiums on edges here. 4 more sodiums on edges kind of in a bottom layer. So I have 12 total sodiums on edges, but the edge is the meeting spot of 4 cubes. So I'd really have like 12 times like a fourth of each of those atoms that's inside our actual cell, which is 3, plus the 1 sodium that's in the very dead center. So it is 4 for my Z plus as well, but just looking at the unit cell can be kind of overwhelming as far as how you can figure that out. So that's why I think always start with your anion, just find the structure type. The structure type helps immediately just give you Z minus the same way we did for our pure metals at the beginning. And then you can get the Z plus by balancing your charges. That's what I think is usually the easiest way to do that. Now, the structure type for our sodium plus ions. This is, remember, paired with the Cn plus. So I think the easiest one to see is the dead center sodium here in the middle. So let me maybe zoom in even just a little bit more on that one. That sodium in the dead center is closest to, it's like this chlorine, this, oops, not that one. That one unselected. So it's closer to this chlorine, this one, this one, this one, that one over there, and this one on the bottom. Which if you're looking at it, happens to be the 6 that are on really the faces. Because as I spin this around, all of your chlorines on the corners are a little bit further away from that 1 sodium in the middle, but all the ones in the faces are the same distance. So this 1 center sodium is touching all 6 of the chlorines that are on the faces. So Cn plus is 6. And remember what I said up above in terms of describing hole types? If our coordination number of our cation is 6, we have an octahedral hole, is the hole type that ion is in. So the description of our structure type for the sodium ion is going to be octahedral holes. R plus over R minus, you can just look at that chart of the ion sizes, and you're just taking the cation radius divided by the anion radius, and you should see this ratio is a good bit smaller than it was for cesium chloride because it's an octahedral hole, not a cubic hole. It means that our cation is a little bit smaller in that case. And the density calculation, I think you can actually look at the pre-lab video, and it gives you a decent walkthrough for that one. And so I think we'll kind of wrap up here at the last little bit. We'll look at our very last example here, and that's for lithium sulfide. And what I'm going to do is I'm going to show this structure, and I'm going to let you guys go through and try to answer these questions on it. And if you have questions and are having trouble figuring it out, like I said, these are the things you want to ask then in your virtual meetings this week. You can ask kind of your instructors and your faculty members to help you out and help you kind of see the things and get these last pieces of information if necessary. But hopefully now that you have kind of an idea of how this is working, you can look at the structure and kind of figure out some of this information. And so the things I'll show here for the structure, this is what our structure looks like. I'm going to hold it at this angle for right now. The actual, in terms of like what's what, the yellow bigger spheres here, that we see kind of on all the corners and things, and also you'll see elsewhere here in the structure as well. Those yellow spheres are the sulfurs, so those are our sulfide ions. The lithium ions are the little tiny kind of like purple spheres that are more in towards the middle. And so your goal for the sulfur ions that are here, the yellow spheres, is to figure out what unit cell type of all the different ones that we've talked about is being made up by these sulfur ions. And then what you want to figure out, that'll give you your Z minus as well. And then you can balance your charges here to figure out what your Z plus is. And then for your lithium plus, it's going to come from your Cn plus, which I'll take kind of a quick zoomed in look here so you can hopefully kind of see that. If this is the lithium I want to look at, I want to figure out how many sulfurs that are all about the same distance from this one single lithium. Well, it looks like from this one lithium, there's this sulfur, this one, and this one. Those four are kind of all pretty close to it. All the other sulfurs are a good bit further away. As I kind of scroll around, you can kind of hopefully see that. And so if that is the case, then you can use the fact that there's 4 sulfurs around each lithium to help figure out then the whole type. But that's, I think, what I'm going to give you for right now. I think this is hopefully a good stopping point. I know this video is plenty long already, but give this video, hopefully, like I said, you can go back and look at anything that you need, but use your kind of virtual lab kind of meeting times this week to kind of help get any questions answered on things that you don't know kind of how to do for these post-lab pieces. This is a good time, I think, this week to try and work these before lab if you can, so that you can just come with questions. Make kind of the best use of your time for your meetings. I'm sure your faculty members, we all probably have kind of slightly different things planned for our virtual meetings, but I think a lot of it's going to be just helping answer questions about how to do certain things, where certain things come from, like how do we figure out different structure types, how do we find things like Z plus and Z minus if we need to go through those things again. But hopefully this video gives you guys a pretty good head start on that. And between this and the pre-lab video, if you've put in the time to watch them, there's not tons of calculations left for a lot of the data table pieces left for you to do, but you will have some good kind of examples in the post-lab for calculations. Also, I think that we'll hopefully check and make sure you're kind of getting the things out of this that you probably want to be able to take away at the end of all of this. But that's all I have for this time. Like I said, try to kind of give these videos a good look through before you go to lab, and hopefully then that'll make things a little smoother in terms of the questions you can ask. But if you do have any questions or running into issues with CSE Pub, feel free to reach out to us and let us help either at our virtual meetings or even outside of them by email if we have to. All right? Have a good one, everybody, and we'll talk to you next time.